Okay, let's begin. So, we rushed through the last example, and I think there was a little bit of confusion, so I actually want to go over it very slowly, because I'm using that example to introduce a new idea called conditional probability. That's important. That's going to allow us to introduce an idea called independence. And that, together with disjoint unions, we can figure out something called Bayes' theorem, which is very important. So let's make sure that we have this idea down. So, starting at the last example, so you roll 2 dice, find the probability. The sum is 10 given that 1 shows a 6. Right? So we already know how to find the probability that the sum is 10. We did that by the table as well as using counting techniques. But now we're given new information. So now we want to find that the sum is 10 under the condition that we already know one of them is showing a 6. Now, here is what we did. We set up our sample space for the problem. So it's all possible pairs of numbers from 1 through 6. So we have 1, 2, 1, 1, 1, 2. I'm not going to list all of them anyway. 1, 3, 2, 1, 2, 2. Dot. So that was our sample space for the situation. And then what we did was we found A, which is the event, the sum is 10, and we saw that there were 3 situations.
I think that means class is going.
We could have that. Now, one of the questions, because we were in like the last 3 minutes or so, that we kind of glossed over is, why don't you have 2 sets of 2 5s? Was one of the questions. And that's because these actually describe the same situation. So one way you can see this is because if I say, okay, the first die shows 5 and the second die shows 5, it's exactly the same thing for me to say the second die showed 5 and the first die showed 5. And if that isn't satisfactory, you might have recalled we actually did the table before that represented all possibilities. And we noticed that the guys where both dice were the same went all down along the diagonal. And you will notice that there was exactly 1 pair for each such situation. Right? So there aren't 2 5s. There's no 5-1 and 5-2. There's a difference between distinguishing between the dice themselves and distinguishing between the numbers that are written on the die. So for us, there's only one situation in which there are 2 5s. I don't have to distinguish which one is giving me a 5 necessarily. Because when I list all possible situations, the guy with 2 5s, there was only one of them in the entire table. Okay? So I didn't have to double up on that. I did have to double up on these though, because these would represent 2 distinct situations. One is going to show up in this location, above that. And then the other one is going to show up in this location. So these are 2 actually distinct situations, so I have to list both of those. So that was the first thing. So that was how many ways you could get the sum being 10. There were 3 distinct ways. Now, we are given the fact that 1 was a 6. So, if I call that B, this is the event 1 dice, 1 die is 6, it shows a 6, then we'd have to list all those possibilities. So, let's just do all of them. So 1 and 6, 2 and 6, 3 and 6, 4 and 6, 5 and 6, 6 and 6, 6 and 1, 6 and 2, 6 and 6 does not get repeated. That was only one situation. And this is, to compare it to one of the first problems that we had, the two children problem where one was born on a Monday, and I said, oh, there seem to be 28 possible scenarios, but really the total was 27, it's because something like this actually happened. Okay, so we didn't actually count that situation twice. And so here, you notice that there are 11 such things, 11 such possibilities. Now, we can reason through this then and say, since we know B occurs, exclamation at the wrong point, our sample space changed. Giving new information means our sample space is going to change. I now know what the actual possibilities are. Before there were 36 total possibilities, but when someone tells me, oh, by the way, one of them is a 6, oh, now there aren't 36 possibilities. It's not possible to have that, for example. There are now only 11 possible outcomes in this scenario. In fact, it changed to B. So now, B is like my new sample space. This, to me, is all possibilities, as far as I know now, when someone tells me that 1 was a 6. So now what I want to do is I want to take a subset of this set that has the sum being 10. Now, I already found all possible ways for the sum to be 10. All I need to do now is know which one of these guys are in those guys. And how do I find that out? Well, I find the intersection. Now, the event we want becomes A intersected with B. I need to know which of these possibilities is within the realm of all total possibilities, in which case the 5, 5 is now no longer considered. And how do I know that's no longer considered? Because he is not in here. Right? So to me, that this guy would not be a subset of that guy because there's something in here that's not in there. So what I do is I take the intersection, and now you'll find that there are actually 2 things. So out of all these possibilities, 2 of them have the sum being 10, namely those 2. So the 5, 5 was ignored, and basically, at the end of the day, we realized that we have this sample space, and that was the event that we wanted. The probability that we wanted is going to actually be this guy. It's going to be the size of the event over the size of our sample space whenever our probability is finite. Now there's another way that we can write this, and that's just to make the formulas nicer, because obviously this situation, it doesn't work well when our sets are infinite, because what does it mean to divide to infinities? So a more general formula would be if we use our definition to get to a probability equation. So I divide both the top and bottom by S, and then each term individually in the numerator and denominator is actually how we defined our probability. So we ended up having the probability of the intersection divided by the probability of B. Now, let's introduce the idea. This is called a conditional probability. It is denoted by so here's how, whenever we want to mention that that's the formula we're thinking of, or some variant of that formula, the notation is this: P of A, we write a vertical bar, And by our definition, that is going to be equal to this. And this part here, we read it a specific way. This is read probability of A given B. Right? So this bar is read as given, right? Probability of A given B. Okay, so what that is, this is the probability that A will occur given that B has already occurred. So this means you're looking for a probability under the assumption that some condition, some previous condition has been fulfilled. This is called a conditional probability, and they are very important. So in the two children's problem, going back to the probability teasers, the first question you could just think of as a general probability was probably that someone who has two children has two girls. Once you start giving someone information, okay, we now know that one is a girl. What's the probability of two girls? I was actually asking a conditional probability. And that's why the answer probably wasn't obvious, because you wouldn't really be thinking in this way at that point. And if I say the older one is a girl, that's another conditional probability. Okay, one of the girls was born on a Monday, that's another conditional probability. So it's a very important idea, because sometimes, based on what events have occurred, the chances of something else occurring will change. And so whenever you have information about something, it can actually change your probability when you want to look at the probabilities. Let us introduce a new idea. Do I want to do that now or a little bit later? Let's do it now. Doesn't really matter which one I do first. The order is not going to matter. Okay, so that is a new kind of probability, probability of A given B. If you want to know what is the probability that some event will occur, given that you know some other event occurred, this is what you have to figure out. Let's look at a very important definition. Now, suppose A and B do not affect each other. That is, one occurring does not influence the occurrence of the other. Then A and B are called independent events. So you're looking at two possible events, but you happen to notice that one is not going to affect the other at all. We call these events independent events. These events are independent of each other. Let's actually try to figure out a mathematical formulation of this kind of thing. How do we know two things are independent? Independent would be knowing B occurred, for instance, would not change the probability of A occurring, right? I'm just writing what I just said in different words. But what does that mean? That would mean so let's say we're in this situation, right? Knowing B has occurred doesn't affect A occurring at all. Like I can compute the probability exactly the same way I would before. What does that mean for this statement? Yeah.
Probability of A given B is the same probability of A.
It's just the probability of A. It's not going to. If I want to find the probability that A is happening, whether or not B happens is not going to matter to me if they're independent. The probability of A happening is just going to be whatever the probability of A happening before, right? Because knowing that B has occurred isn't going to matter. So we have that is true. Now, by definition, that means we know that the probability of A given B is equal to A intersect B over the probability of B. And so this implies if A, B are independent, what is going to happen is that this thing, which is equal to that thing, is going to equal to this thing. This would mean that the probability of A intersect B over the probability of B, which we know that's just another way of writing P of A given B, that is just going to be equal to P of A. But that will mean that the probability of the intersection is the product of the individual probabilities. Now, there have been several times since we started probability where I'll just throw out a question there. So what do you think the probability is going to be? And so every now and then, a student will raise their hand and say, oh, it's going to be 1/2 times 1/2, right? Like they multiply probabilities. Sometimes they were right, sometimes they were wrong. Now we know why. Whenever the product of probabilities doesn't give you the answer that you want for the intersection, what it means is the two things you were talking about were not independent, right? So there are going to be times, and that's a very knee-jerk reaction. A lot of times students think of and as multiply when it comes to probabilities. This is not true in general. You can't just multiply probabilities whenever you want. You can multiply probabilities to find the and probability if you know the events are independent. That's the only time this equation is going to work out, right? So pretty much every time you said, oh, you just pick 1/2 times 1/2, right? That's the answer. And I said, no. What that meant was the things we were looking at were not independent. One actually affected the other. Now, that is worth actually writing down as a thing. So, as a box statement to remember. A, B, independent. Means there are two ways we can classify independence in the mathematical sense. The probability of A given B is going to be the probability of A. So that's one thing that it would mean. Another thing that it would mean is if you want to find the probability of A and B, the intersection between the two events, this will be the product of the probabilities. Now, of course, this is going to be a symmetric relationship. It's also true for me to say that the probability of B given A is going to be the probability of B. But I assume that's understood. But this is something that you should know and be very careful with, because it's often a knee-jerk reaction to multiply probabilities whenever you hear, oh, this and that is happening. Students like to multiply automatically. These equations do not hold unless independence is achieved. So, if you know that two things are not independent, one affects the other, or let's say you have no idea, they might affect the other, but you're not sure, you have no business multiplying probabilities. Do not do this unless you have independence. Okay? So that is a very important lesson. Don't wantonly multiply probabilities. You have to have independence to have a multiplication work out for this thing. So that's the first important statement. There's one that I mentioned before that I think bears repeating. And sometimes these two are mixed up, but they're actually very different things. We also have ABR disjoint. Sometimes in the language of probability, we call these guys mutually exclusive. Now remember what mutually disjoint meant? It means the intersection was the empty set. So if the intersection is the empty set, what's the probability of that? Well, it's going to be the size of the empty set divided by the size of the sample space, which is going to be 0. So when two events are disjoint, meaning they cannot occur at the same time, what that means means probability of A and B is 0. The chances that both will occur at the same time is 0. There's a 0% chance of this happening. When you flip a coin, you cannot get both heads and tails. We say heads and tails are mutually exclusive events. They exclude each other. So that's a very important thing. Also. So, this also means, so there's another thing that this means, the probability, and this is also something that students do whenever they see or when they shouldn't. The probability of the union is just the sum of the probabilities. Now that follows from axiom 3 of the probability axioms, but yeah, that's what we have. Now, I do want to mention also what you need to know. Doesn't matter what order you memorize these in, but you need to know all of them at all times. In general, what is the equation that governs and versus or? Well, the law of disjunction. So in general, that's what governs them. If you want to find the probability of A or B, you have to add the probabilities and minus the probability of the and. If you want to find the probability of A and B, well, you just solve for it in this formula. You add the probabilities and subtract the probability of the union. So that is in general. However, in two very specific circumstances, and is translated as multiply, or is translated as add. Right? So these two are not always true. They happen in very specific circumstances. This one is true in general. That's always true. But be careful when you're adding probabilities and you're multiplying probabilities. You need to make sure you are in the right situation. This one tends to be more obvious. That one isn't. Usually it isn't obvious. There are times when things might depend on each other that you would never think would actually depend on each other. So this isn't obvious at all. So definitely be careful with this a lot. This one usually is going to kind of be obvious, right? So you flip a coin and you draw a card from a deck. What is the probability that you get a queen given that it landed on heads? Well, it's just going to be the probability of getting the queen in the first place, right? It doesn't matter what the coin is doing. They're totally disjoint situations, right? So things like this will be obvious once you understand that you're in this situation. The two events that you have nothing to do with each other. See, even I'm messing up now. That's the incorrect statement to say. Once you know that the probability of both things happening at the same time is 0, this equation takes effect. Once you know that neither thing has to do with the other, like one occurring doesn't affect the other occurring, this equation takes effect. They do not take effect otherwise. This is the one that takes effect under all circumstances. Okay? So that you can always think is true. These are only true in 2 different situations. And I'm harping on this for a reason. It's a very common thing to actually mess up with. So normally when you hear something like, oh, what's the probability that the first one is a girl and the second one is a girl? People automatically think, oh, you multiply them, right? You have to be careful. Just because you hear and doesn't mean multiply. So yes, those are 2 very important, 3 very important ideas. Do I want to do an example now? I have another important idea, but I probably want to do an example first. Okay, let's look at this problem. You guys have all of them. So mutually exclusive, they cannot happen at the same time. This means the probability of the intersection is 0, and the probability of the OR is the sum of the probabilities. Independent means they could possibly occur at the same time, but one will not affect the other. And so that means that the probability of A given B is the probability of A, and the probability of the AND is the product. So let's say you take a standard deck of cards, you pull out all the aces, right? So you have the ace of hearts, the ace of clubs, the ace of spades, the ace of diamonds. You draw 2 aces at random. Let A be the event, the ace of clubs and the ace of spades is drawn. Let B be the event, the ace of spades is drawn. Are A and B independent? So that's a question I would ask on a probability test from time to time.
Wait, which one?
So I will describe 2 situations to you, and the question would be, are they independent? And sometimes it will be kind of tricky if you try to use your common sense, and you don't want to use your common sense. You have to know what does it mean mathematically to be dependent, and then you're going to just check, do the equations work out? So forget what you feel, that's often going to be wrong when it comes to probability, and we'll actually look at that when we talk about Bayes' theorem again, why probabilistic thinking is important. Oftentimes your intuition is going to lead you astray if you're not careful. So forget what you feel, how do you actually work this out? So now, one thing you want to do is you want to already have in mind to show A and B are independent. We need to show either the probability of A given B is the probability of A, or the probability of the intersection is the product of the probabilities. Now either one you show is fine. It would often depend on the problem which one is actually easier for you to get to, but you should know whenever you want to determine whether things are independent, you need to verify one of these 2 equations. Right? So at the end of the day, whichever one is easier for you to pick out of the problem, that's the one you're going to use, but it's either or. You need to show, oh, this equation is true, therefore they're independent, or that equation is true, therefore they're independent. So that is the background. So how do you go about doing this? Let's put this all together. So let's find these probabilities. What do you think? So forget about the independent part. Just worry about finding the probabilities of the A and the B, or the A given the B, whichever one. How do you start? Yeah?
Choose what A, C, and AS are.
Huh?
What is A, C,
Oh.
and AS?
So, this is the ace of clubs,
Oh.
and this is the ace of spades. This is the ace of spades. And but I can't bother drawing the thing all the time. So we'll use AD to mean ace of diamonds. And what's the other one? Ace of
The
hearts. AH means ace of hearts. So I pick two cards at random. What is the probability that the two that I pick is the ace of clubs and ace of spades specifically? Or another situation, what is the probability that one of the things I picked was the ace of spades? Right? Those are the two events. Are they actually independent? Would one actually affect the other? So, yeah, how would you go about solving that problem? Yeah.
You start by doing the sample size. Like
Right, you try to figure out the sample space. It's always the first thing you try to do. How am I going to dissect this problem in my head? How am I going to think of the objects that I'm moving around that I'm looking at? So the first thing you want to do is figure out what am I going to look for in the sample space. How is that going to look? Now, again, there's a way here to pretend order matters and either order matters or order doesn't. But pretending that order does not matter, you always have smaller numbers. You would always have less sets that can be created than tuples. We already showed why that was. Because tuples can rearrange and get a different tuple, whereas sets, if you rearrange them, it's the same set. So I probably put them in, yeah.
Are you putting the ace of clubs and the ace of spades back in before taking?
No, I draw two at the same.
So, and then when you try to draw, so you're not replacing it?
No. So that's the random experiment. Someone picks two. So one situation is they pick the ace of clubs and the ace of spades. And another situation is one of the things they picked is the ace of spades. Right? So these are two scenarios.
Okay.
I want to know, does one of those scenarios affect the other one happening? So you could worry about order, but let's say I don't want to worry about order here. So I'm just going to think of the cards I pick as sets of cards. Right? So, for example, I could get the ace of clubs and the ace of spades, regardless of what order I pick them up in. Or I could get the ace of diamonds and the ace of spades. Or I could get the ace of clubs and the ace of diamonds. Or, etc. Yep, so I could have that. What would be the size of this? So I have a set of 4 things, and I want to create sets of size 2. How do we count such things? Yeah?
4 times 3.
No?
Is it 2 or 4?
No?
This is 40.
Are we just randomly get, like, it's going to be one of these, so you say this one, I'll say this one, I'll say this one. So the 4 times 3, that would be in the situation where I'm thinking of this as stages and I'm using the multiplication rule. I'm not thinking it's one thing. I'm drawing 2, so I'm not thinking of it in stages. The 2 to the 4, that's when we're counting all possible tuples that include repeats, which clearly can't happen here. So it wouldn't be 2 to the 4. What I want to do is I have a set of 4 things. I want to choose 2 random things without order. That's combination, by definition. This is going to be 4C2. So that's going to be 4 times 3 over 2 times 1. So that's going to be 6. There are going to be 6 things in this set. Now, if I'm looking at set A, what would A look like? Well, A would be, well, there's only one thing in A. I have to pick the ace of clubs and the ace of spades. So A has one thing in it. There's only one possibility under which I would have achieved A. What about B? How many things are in B? So B was the ace of spades is chosen. Right? So what are the things here? How many things are there? Huh? You can start just listening to the possibilities if you don't see it right away. If this was a test and there was 5 minutes left, don't try to think of a clever way. If you can't think of what it is, just start listening. Yeah. What's one of the possibilities? Yeah, could take the ace of spades and the ace of diamonds. Other possibilities?
Ace of spades and ace of clubs.
Ace of clubs. Other possibilities?
Ace of hearts and ace of spades.
Ace of spades and ace of hearts. Other possibilities?
That's it.
That's it. There are only 3 possibilities, right? So the ace of spades is chosen. There are only 3 other aces. So there are 3 choices that I have to put in a set with this guy. There are only 3 things here. So now let's look at what we want. Now, given that that's my sample space and that's the size, you can also notice here the size of A is 1. Here the size of B is 3. So, what is the probability of A and B? Well, that's going to be the size of A intersect B over the size of the sample space. What is the size of A intersect B?
1.
1. What is in the intersection? Well, this guy. That's the only guy that's in the intersection. There's one thing. What is the size of the sample space? We already found that. That is 6. So the probability of both occurring together is 1/6. Now I want you to fully appreciate. I did not find the probability of A and B separately and multiply them to get that number because I don't know ahead of time whether they affect each other. Multiplying the probability would not be something I would do. I would go back to basic principles, find the probability the straightforward way by the definition. Now, if I were to go find the probability of A and the probability of B separately, well, by our definition, that's the size of A over the size of the sample space, that's 1/6. If I were to find the probability of B, that's the size of B over the size of the sample space, that is 3/6, or 1/2. Now, the question is the probability of A intersect B equal, question mark, to the probability of A times the probability of B? No. What does that mean? It means they are not independent. It means if you were to do this and multiply them and think that that was the answer, you would be incorrect. Oh, we can find how we can get this and we can find how we can get that and multiply them. For some reason that feels intuitive to a lot of people, but it would actually be the incorrect thing to do here. A and B are not independent. One does actually affect the other. And how do I know? Well, a couple ways we can see that. We can see here, there were 6 total possibilities. For A to just happen by itself, that's 1 out of the 6 possibilities. If someone told me B already happened, now the total number of possibilities reduces to 3. The denominator of my probability automatically changes. Now getting the A to happen is going to actually be easier. I'm choosing from a smaller group of things. So they wouldn't be independent. One would actually affect the other. If I know B happened, it definitely changes the chances of A happening, because the chances of A happening will go from 1/6 to a half, to a third, right? So knowing that one happened will actually affect the other one happening. So these are not independent, and it would mean that multiplying the probabilities to find the AND would actually be incorrect.
Good drill. Every time we go.
Well, we had 5 minutes left. I can do a lot. You guys know I can do.
Oh, yeah.
But all right, gotta be safe. I'll see you guys Friday.